It's a pleasure for us to start this edition of the PRISM Prize.
2021, Matteo Vitrano, Harvard University, USA, Valeria Nicolosi, Trinity College, Iowa.
2022,
Stefania Gallo, CNR-ISM, Riccardo Comini, MIT, USA.
2023,
Nicola Gasparini, Imperial College London, UK. Federico Capastro, Harvard University, USA.
2024,
Nikita Cavochini, EPFL, Switzerland. Alan Aspurubusic, University of Toronto, Canada.
Receiving such a prize for me means the world, so thank you very much.
Received this award by my national community.
For this award, thank you to the CNR-ISM for the PRISM.
It's a true honor to receive this prize. I was very, very humbled to receive this prize, and thank you. No.
Thank you very much for the award and the
CNR, Istituto di Struttura della Materia. Innovation is part of our life. Carries out fundamental and applied research on matter using cutting-edge experimental, theoretical, and computational approaches. From solid-state physics to materials chemistry, from nanotechnology to optoelectronics. Our research drives innovation in the fields of energy, health, environment, and technology. What makes a solar panel more efficient, or a computer faster? The answer lies within the matter itself. At CNR-ISM, we'll study how materials are made, down to the level of atoms, because understanding the structure of matter means being able to design better materials, from the engineering of 2D materials to the physics of semiconductors and low-dimensional systems, all the way to developing new methods of characterization with atomic resolution. We work in synergy with major European infrastructures, universities, research bodies, and industrial stakeholders to transfer knowledge and innovation in the fields of energy, photonics, electronics, and advanced materials. With locations from the north to the south of Italy, CNSM brings together expertise, state-of-the-art instrumentation, and scientific curiosity to build the future.
Welcome everybody. So we are ready for the new edition for the PRISM Prize, and let me just welcome Dr. Stefano Fabbris, which is the director of the department. So we are the department and several institutes of physics, and now the director of the Department of Physics, Stefano Fabbris. Welcome.
Thank you, Aldo, and welcome everybody. Welcome to the awardees of this very inspiring prize that you put up. Congratulations. It has, from my perspective, it is a very important initiative. It gives a lot of visibility to the institution, to the institute, and yes, so on behalf of the National Research Council, welcome to everybody. And I've been asked, beside these greetings, to provide a short overview of what we are doing at the department, who we are, to the benefits of the awardees, let's say, but also to the people that maybe are younger and do not know precisely how we are articulated and what we are doing. And I can start from very far, from very deep in the past. So we have celebrated 2 years ago the 100 years of the National Research Council. It was instituted by a decree of the King of Italy in Rome as a moral institution. And the very first headquarters were at the Accademia dei Lincei in Rome. Of course, I don't want to drive you through all the history. I just want to make the point that physics was somehow at the heart of CNR since its foundation. So, of course, here are some iconic points. Of course, Guglielmo Marconi, the second president of CNR, and first Italian Nobel Prize in physics. During his presidency, Enrico Fermi actually essentially had my position. He was the head of the CNR physics committee, and later on he got the second physics Nobel Prize for Italy. And more recently, Giorgio Parisi, you all know him. He's associated. Well, he had a scientific growth in part at CNR, and is still associated with the Institute of CNR. Let's move fast forward. At the present day, this is how the Department of Physics is organized in strategic areas that covers from physics of atoms and photons, advanced materials, sensors, so through the spectrum from atoms, let's say, to applications, complex systems, which is an emerging field, as you all know, biophysics and plasma physics, that is somehow important for the applications on nuclear fusion which are overlooked by the department. These strategic areas are the playground of several institutes, and the Institute of Structure of Webs. The structure of matter is here, so that somehow each institute has a center of gravity in one of these strategic areas, but is spread transversely, may be spread transversely to many of them. So there are institutes that are somehow multidisciplinary. So this is just a representation. What I want to point out is that these 12 research institutes constitute a network, a valuable network that talk to each other, connect to each other, and constitute somehow an ensemble of competences that put together about 1,000 of researchers. And this is used to essentially to shorten, one of the main goals of our research is to shorten the innovation chain. So through this network, we try to connect fundamental research, applied research, down to the technology transfer and industrial research. And this is done not alone by this network of people, but is done and is done also thanks to the strong cooperation with the Italian and international academics. We have more than 300 associates from academia to the institute, and on the other side of the value chain, this is done also with the strong presence and connection with the private sector. I will show some example later on. Of course, we try to be strongly aligned with the European strategies and with the Italian strategies, the national strategies that are somehow aligned themselves to the European strategies. So we participate also in the governing bodies of several joint undertaking or associations that define and drives the strategy at the European level. The Innovative and Advanced Materials Initiative. I was in Brussels last week for the first meeting of this. We are part of CHIPS JU, of course, the Euro HPC, and I'm sure that each of you can reconnect to at least one of these main institutions. As an example, we are present in the digital roadmap of the European Union. You know, this is defined in 6 main pillars, from superconducting, hyperconductivity, quantum technologies, and so on. So the department is strongly involved in each of them, as it is also demonstrated by the projection of this European strategy to the national strategy that was put forward with the recovery funds. So this is somehow a projection of some of the initiatives that they were set up with the recovery funds, in which the institute of the department play a major role, from the National Center for High Performance Computing, infrastructures for research infrastructure for quantum technologies, main projects on quantum technologies, quantum computing, of course, several initiatives on artificial intelligence, and for the semiconductor technologies, we have both regional ecosystems and infrastructures. We are not too bad with publications. We publish more than 2,000 publications per year in major journals. So this is aligned, according to my statistics, with homologues institutions that are at the European level and that receive much more public funding than it's available in Italy. We are active in many key sectors, but I can say from a quick analysis that in at least 2 sectors, like material science and applied physics, we are the national reference when you compare it to all other production, even if you scale it with the number of scientists in the institution. Another very distinct properties of the department is the attraction or the creation of ERC projects. So these are the ERC projects that are active now, and this is the only department that can somehow show this kind of success, and this is really thanks to the researchers, younger and older, that work hard in the institutes. By the way, there has been the results of FIS projects, let's say the national equivalence of ERC, just last week, and I don't have the slide yet, but the department has somehow the lion's share also on these projects. So all in all the institutes are very lively in funding. We are at the department see more than 2,000 active projects with an overall funding in external funding of more than 300, almost 300 million. I was saying this is somehow the array, the matrix, the strategic areas, the institutes, but all of this is also sustained by research infrastructures, expertise in designing, managing, rethinking, and making available national and international research infrastructures. So this is just as more selections, though the S3 landmarks for the synchrotron radiation sources, neutron sources, laser sources, free electron lasers, or high power laser sources. At the national level, I was talking with one of the awardees. Actually, the Institute structure of matter is strongly involved in this one here. CNR is the main partner of Synchrotron Trieste, the national synchrotron radiation source, where we manage 10 out of almost 30 beamlines. So a third of the synchrotron is managed by CNR, and this is now undergoing a very important upgrade in which, again, the Institute of the Structure of Matter is strongly involved. Not only research infrastructure, but we are moving towards technological infrastructure. So this is the picture of the event that was held in Brussels at the beginning of this year. That is the launch of the first 4, actually there were just 4 here, the 5th joined in later on, pilot lines that were financed by the CHIPS Act. So the CHIPS Act is this initiative that aim at bolstering the semiconducting sector at Europe. A lot of funding available, almost 43 billion up to 2030. The first round financed 5 pilot lines, supported with almost 4 billion. One of it is coordinated by CNR, actually by the department. It will be built, well, it's a distributed facility, technological infrastructure, but it has a very strong center of gravity, which is in Italy, in Sicily, close to the ST Microelectronics plants. And the main investment is oriented to build wide, very large clean rooms dedicated to the front end part of semiconducting industry and the semiconductor growth, somehow trying to bridge the prototype that can come out from a lab to the production of several these devices that are based on that prototype. And this somehow closed the cycle. I was mentioning that the final part of the chain of value that is promoted and by the department is that industrial production and some of the institutes of the department are really integrated with industrial settlements like ST Microelectronics, Leonardo, both physically or with strategic projects, and this somehow result in a very rich portfolio of patents and industrial partners. So with this, I'd like to conclude and congratulate again with the awardees of this year, congratulate again with Aldo and all the people that are following this initiative that I think is very, very, very important. And also I take the opportunity to say Merry Christmas and Happy New Year to all of you.
Thanks a lot, Stefano. It's very nice to be part of such large infrastructure, such large department, and we are very proud to contribute to these activities and the success of the department. I took just a few seconds, to just say something maybe new about the institute. So this is the institute. Institute of Structure of Matter. We are divided. We are present in 4 sites. The main one is in Rome. The second one is still in Rome, but the north part of Rome. And then we have the synchrotron activity that Stefano was mentioning in Trieste. And then also we have another site, which is in Potenza, actually, Tito Scalo. So our mission, you see, is to develop material, but also to have a look to the sustainability of the materials. And then starting from the synthesis to the characterization and also to the use of these new materials for new complex applications. So for this reason, we conjugate the concept of structural matter for different applications. And then you see there are some applications like you see biohealth, security, ICT, energy, automotive and aerospace, cultural heritage. But we keep very alive the blue sky research. We want to keep it as an important asset of the Institute. So we provide support for those who are really want to explore without having in mind a clear application, the potentiality of material research. So this is something that we are promoting more and more among all the participants and all the associates to the Institute. One of the important things also we did during this year is to create a backbone of a platform, a technology platform of the Institute. So we made a lot of work to put together in a story, in an ecosystem, all the characterization, synthesis, theoretical instruments, and also prototyping activity to offer to the community, the internal community of the Institute, but also to external community, the technology platform. So now you can access the platform easily, and then you can really use this platform for the developing your science, the best science you have in mind. So there are more than 130 tools that you can use, and then I believe every day, but it's not every day, but we are adding new tools to foster more and more this technology platform, which we call PRISM. So just two examples. So one was already mentioned by Stefano. We contribute to the development of electrosynchrotron in Trieste, and we are now in a very exciting phase. Now the synchrotron stops for a revamping, and we are moving from the electrosynchrotron to Electra 2.0, where we merge the 3-line in 2-line, one dedicated to low density matter, gas phase, other related low density. Another one is something which is related to low dimensional laboratory. So one of the main objects will be a momentum microscope that will be aligned, connected to the synchrotron radiation. So this will be a very important asset for the Institute. Another one which is very modern is to develop a material and device acceleration platform. So we set up this platform from the synthesis of material completely automatized with robots, and till to the film deposition, characterization, and also final device characterization. This is what we are setting up, and is still not ready. Will be ready in February 2026. So I book already Stefano for the inauguration of this platform in February. And but very interesting also is that we can create a lot of data, and then the use of this data, and then to use machine learning, artificial intelligence algorithm to handle this data will be a very important boost for the Institute and for what we can contribute to the material development. So now let me move to the central part of today, the PRISM Award. Okay, so let me just explain in a few words what is the PRISM Award. So, the Institute was established, this PRISM award in 2021 for scientists having achieved outstanding breakthrough in the past 5 years. So it's really, it's not a prize to the career, but it's a prize to what you are really doing now, how you can contribute, how the scientists are contributing now to the state of art, defining new state of art, new knowledge in the field. So, and we have 2 categories. One is junior, which is below 35. Another is a PRISM senior for those who are aged more than 35. How does it work? How is the process? The process is the following. So we start almost in March to make a call for nomination. So we spread all these requests for nomination everywhere in the world, and then we launch this nomination many times till more or less this June. Then everything goes in a jury, international jury, which is formed by those who already won the PRISM Prize in the last editions, plus the site managers of the CNR. So the director is not taking part about the jury, so I'm really completely out of the system, but I take the system working on. And then after this the analysis of the international juries, we make a ranking, and then we select the 2 in the 2 categories, the PRISM, the senior and the junior. Let me show you who was winning. So the first one, when we started in 2021, was prize was given by Valeria Nicolosi and Matteo Mitrano. Valeria from Trinity College of Dublin and Matteo from Harvard University. The second year, so the junior was Stefania Kakovic from CNR-ISM in France, and Riccardo Comin from MIT in USA. Coming now to more recent years, so in 2023, the junior category was awarded by Nicola Gasperini from Imperial College of London, and the senior category from the great scientist, Italian scientist, Federico Capasso from Harvard. Last year, we had the junior categories was Nikita Kavokin, was from APFL in Switzerland. Actually, was coming also from the Max Planck before, but now he's in APFL. And the senior category was awarded to Alan Aspuro-Gudzik from University of Toronto of Canada. So now I see that, you are now looking who will be the winner of 2025. So this is the official announcement. So we already made a lot of announcement on the web and some other media, but it's really a pleasure to nominate now, to congratulate with all of us, to congratulate with the new winners of the PRISM 2025. So I want to say for the outstanding breakthroughs achieved by these people, these 2 scientists in the last 5 years in the field of science of matter. So for the junior category, it's really a pleasure to award the PRISM Junior to Wouter van Kompel. Wouter is assistant professor at Hasselt University in Belgium. And for the senior category, it's really a pleasure to award the PRISM senior category to Kim Fai-Mak from Max Planck Institute. So that's really a pleasure, and now we have 2 PRISM Award lectures. So the first PRISM Award lecture will be given by Wouter van Kompel, and then is related to explore a synergy between the organic and inorganic components of low-dimensional allied perovskite, tuning optical and electronic properties. And then the second lecture will be given by Kim Fai-Mak how a Moret pattern creates magic in semiconductors. So it's really a pleasure to welcome here the first speaker, the first award lectures from Wouter. Wouter. You want to use this or it's okay? This one? Or the other one?
No, maybe not.
Yeah.
So, is this on? Okay, so it's really my great honor and privilege to receive this award from your renowned institute, and of course to present the work of my team, because it's always a team effort. So as Aldo already introduced, I'm Wouter van Gompel. I'm an assistant professor at Hasselt University in Belgium. So for those who don't know, the location of Hasselt University, it's located in the east of Belgium, so close to the border with the Netherlands and the border with Germany. It's not the biggest city in Belgium, but it's a very nice place to visit. So Hasselt University is a quite young university. So we celebrated our 50th anniversary 2 years ago. But yeah, we are an ambitious university, and we are quite young, which also means we are still a quite dynamic university. So it's a very nice place to visit. So my research group is part of the Institute for Materials Research, IMO-MEC. So it's an institute affiliated with Hasselt University on the one hand, and the Institute for Microelectronics, IMEC, in Belgium, which is well known for the development of chips, for example. And yeah, we try to cover the development of new materials in several pillars. So energy, circularity, health, and also quantum computing, for example. And we have the ambition to work from the design and the modeling of the materials all the way to the reliable device and everything in between. So we have approximately 200 researchers in the institute at this moment. So yeah, one of the research groups belonging to a bigger unit, materials research chemistry unit, is my research group, Hybrid Materials Design. So it was founded now more than 10 years ago by the previous group leader, Professor van der Zande. And since now a little bit more than 2 years, I'm the main group leader. So we are a quite young group. We now have 7 PhD students and 1 postdoc. And some of the work I will show today is done by the people on this picture, and some, of course, by the previous group members. So as the name says, Hybrid Materials Design, we are mainly working on the synthesis. So we are really a chemistry group. We try to synthesize new materials, hybrid materials, and one of the hybrid materials that we're looking at are the hybrid organic inorganic perovskites. Some of you may have heard about them. So yeah, first, of course, what is a hybrid perovskite? So hybrid perovskites belong to the bigger class of perovskites. It's a very big class of materials which all share the same general formula, ABX3, with a well-known crystal structure composed of octahedra, with in general B metal ions inside of the octahedron, and then X ions at the corners of the octahedra, and in the middle you have a bigger cation, A cation. So in case of the hybrid perovskites, the center cation is an organic molecule, typically an ammonium cation, like the methyl ammonium, the one you see on the slide. And then the metal is typically lead or tin, sometimes germanium, and the X is a halide. So it belongs to the class of the metal halide perovskites. And these specific components are also called 3D, three-dimensional hybrid perovskites, because yeah, the octahedra are connected along 3 all three dimensions and three directions. I will come back to that later. Of course, if there are 3D perovskites, there are also 2D and 1D and so forth. So yeah, why are they so interesting? So you could say that they are quite exceptional semiconductors, especially for optoelectronics. So why is that the case? Well, firstly, they have a very high absorption coefficient. So if you compare it to silicon, which is of course still the reference in the relevant wavelength range, yeah, it has a much higher absorption coefficient, which is linked to the fact that this is a direct cap semiconductor. And it, of course, has the advantage that you can go to much thinner absorbing layers and still absorb the same amount of light. So you can start thinking about applications like flexible solar cells, for example, because you can really go to 300, 400, 500 nanometer thick absorbing layers, which is, of course, very interesting towards applications. Then another very important point is the defect tolerance, which is maybe even more important. So why do we say that these materials are defect tolerant? When you compare them to the classical semiconductors like gallium arsenide, cadmium telluride, silicon, and you look at this very simplified band structure, you see that yeah, the atomic states are actually located inside of the band gap, which means that if you get defects like vacancies, you will get deep trap states. And of course, yeah, because they are deep traps, they are not easily detrapped, so they really act as trap states for the electrons, and they also have a quite high scattering cross-section for electrons, which is not what you want. The perovskites, on the other hand, they have a quite specific band structure with the iodide 5p and the lead 6s contributing to the valence band maximum, and then the lead 6p and the iodide 5p contributing to the conduction band minimum. And you see here that the atomic states are either inside of the band or very close to the edges. And that is interesting because, yeah, even if you do have vacancies, they generate quite shallow traps. And yeah, they can just be detrapped via thermal energy at room temperature. So that's one of the reasons why you do not really need to use a clean room to get a very nicely working device. So the processing conditions can be quite dirty, let's say, especially compared to like telluride, silicon, and so on, and still give very highly functioning semiconductors. So that's really a huge advantage. Of course, typically the devices still work better if you eliminate as much as possible defects at surfaces and things like that. But in general, they are quite defect tolerant, which is a very nice property for a semiconductor. So this also means that they can be processed using relatively facile deposition techniques like solution-based spin coating at small scales, but also blade coating, slot die, spray coating, and even printing on the one hand. And on the other hand, they are also generally compatible with vapor deposition, such as single source co-evaporation and so on. So you have quite a variety of deposition methods available for these perovskites. And yeah, what they are most well known for is their tremendous increase in the efficiency of their solar cells, called perovskite solar cells. This has been not seen before, such a rapid increase, of course, learning from the development of all the other solar cell technologies. But still, on a small lab scale, they now rival silicon and even surpass them. And of course, then the great challenge is upscaling. But even there, over the last years, many companies and institutes have made huge progress. And now they are entering the commercial stage, let's say. So that's really a huge success story of the development of these semiconductors. But of course, if you make a semiconductor for solar cells, you can also think about all the other potential applications in optoelectronics, like light-emitting diodes, photodetectors, lasing, neuromorphic devices, and so on. So this boom in the solar cell field has led also to a widespread use of this class of materials in many different types of optoelectronic devices. And that's also the interest of my group, let's say, in these materials. There is one caveat, or there are a couple, but there is certainly a stability challenge because they are ionic materials. It's an ionic structure, this metal halide structure, ionic structure, which means that in general they are quite sensitive to influences of moisture, intense light, like intense lasers, high temperatures, and even electric fields, because these ions tend to be quite mobile. So that's one of the big challenges. People have, researchers over the years have, of course, improved enormously the stability. So they were known as really, really unstable. But over the years, material development and encapsulation and things like that have really improved the stability enormously. But still, it remains an somewhat intrinsic challenge of some of these materials. And one of the potential solutions is reducing the dimensionality from 3D to 2D. So conceptually, what you do is you remove these small cations, and you open up the structure and you insert bulkier organic cations. Of course, it is purely conceptual picture. With the bulky cations, the 3D structure cannot form anymore, and the layers are forced apart. And then you get a 2D inorganic framework. But the bulk of the material is still a bulk material, so we are not looking at morphologically 2D materials. They are still they are structurally 2D, let's say. And that's really the main focus of my research group, because it also involves a part of organic synthesis. So our group is a combined group of chemists, on the one hand, inorganic chemistry and organic chemistry. And with these 2D perovskites, you can really insert more complex organic molecules. And then, there's also an interesting subclass of materials, which are called the multi-layered hybrid perovskites. So in between the 2D on the one end and the 3D on the other end, you can make variations, let's say. You can change the number of inorganic layers per organic layer from NS1 for the pure 2D to NS2, NS3, and so on, by playing with the ratio between these small organic cations, the typical A site, and then these bulkier organic cations. And they have then properties in between the pure 3D and the pure 2D in terms of band gap and electronic mobility and things like that. So there's a quite large playing field in that class of materials. So, okay, for now it's quite schematic still. So what is this organic cation in general? So you have an organic core, which can be quite varied. You have a spacer, an alkyl spacer, which you need because of steric effects. You cannot put the bulky organic too close to the inorganic layer. And then you have an ammonium head group. And this ammonium head group is essential to tether the molecule to the inorganic framework via hydrogen bonding and via Coulombic interactions. So the real focus of my group, let's say one of the two focus points, is trying to make this organic layer functional. So in many cases, it just has a structural component and it forces the inorganic layers apart, but it doesn't really do anything. And that's what my group is looking at, trying to make it electronically or optically functional. So what we are thinking about is charge and energy transfer processes, charge transport, luminescence from the organic, so energy transfer to the organic, and then fluorescence or phosphorescence, enhanced stability, very important, and recently also quite some interest in making the organic chiral, and then you get some interesting circularly polarized light emission, for example. So that's some of the things we are working on at this moment. So over the years, we have synthesized many different organic cations, just to give you some idea of what they are. So these are some examples of molecules we synthesized for very different reasons, for energy transfer, charge transfer, stability, with the fluorinated organic cation. So we are really a synthesis group, let's say, and we try to design the molecules with a certain application in mind, and that's the final ambition. What we also do, being organic chemists, is work on interlayers for perovskite solar cells. So for example, these self-assembling molecules, phosphonic acids, are quite popular now in the literature. Many people are just using this 2-pax, which is the reference or carbazole molecule. So we prepare different ones with a much better coverage of the ITO, the ITO layer, which was a big problem with the literature reference. But I'm not going to go into detail on this part of our research line because of limited time, of course. But that's also something that we do, really organic synthesis of molecules. So on to some very specific examples. So 2D perovskites with electroactive organic cations. So what do I mean with electroactive? Well, in general, what you have, the typical situation is a type 1 internal band alignment, energetic alignment between the organic and the inorganic. So which means that all the interesting processes happen on the organic. Once you excite the material, the charges remain on the inorganic. The organic has a much too wide gap to play any role in the process. But by carefully tuning the composition of the organic and the inorganic, you can get all the types of alignment that you also have in the typical heterostructures. You can think of it as a kind of heterostructure, but then internal to the material. And most are the typical are the type 1, but we also developed a couple of them that are the type 2 interface, where you get really separation of the hole and the electron over different layers. An example that we published in 2023 in JEX, together with colleagues from the University of Cambridge in the UK, was based on this carbazole organic molecule. And the interesting thing there is that the highest occupied molecular orbital of carbazole is above the valence band of the inorganic framework, while the lowest unoccupied molecular orbital is above the conduction band. So you get the type 2 staggered alignment. And it's one of the first examples of that class. So what we did is we synthesized different variations of this carbazole molecule with different tail lengths to study the influence of how close the molecule or the car comes to the inorganic framework, and then on the rate of the charge transfer process. So some basic characterization, XRD, just to prove that we have the material, an absorption spectrum with a very typical excitonic absorption peak, because these materials are excitonic. They absorb and they form electron-hole pairs. And the most interesting thing here is the PL, the emission, where you see it's normalized, that it's progressively being quenched. So the shorter the space it becomes, the more quenched your photoluminescence. And of course, if you get charge transfer from the organic to the inorganic, or from the inorganic to the organic, you separate the electron and the hole, and they can no longer recombine. So you do not get emission from the recombination. So this quenching of the photoluminescence is a good signature for the presence of charge transfer in these materials. So we, together with the people in Cambridge, we did a detailed spectroscopic study, femtosecond transient absorption spectroscopy, and there we see a photo-induced absorption peak of the carbazole cation radical, which is a signature of the fact that this charge transfer has occurred. So this is a real direct signature of photo-induced charge transfer in these materials, which was this direct proof, let's say, was the first time that it was shown in the literature. Next to that, we also showed the presence of a charge transfer exciton, so really a combined state of the organic and the inorganic. So in the absorption spectrum, you get a new CT band, and if you excite that one, you also get, again, carbazole cation radical photo-induced absorption. So yeah, some interesting combined organic, inorganic properties in this material. So why is it interesting? Well, one of the problems with the 2D in general is that you have a very low electron and hole mobility out of plane, because the organic acts as a barrier. But in this case, if you make the organic functional, you get orders of magnitude higher electron and hole mobility in these materials. Okay, they are still quite far from the inorganic, but we are making progress there in designing the right organic molecule to improve the hole and electron transport in these materials. So yeah, it's really an example of how the organic can improve or be important in the electronic and optical properties of these materials. So that's one important component of our work. The second important component is the stability. So as I mentioned, these are known to be relatively unstable, this class of materials. But if you tune the molecular structure of the organic in the right way, they can actually be very stable materials, relatively speaking. So the typical organic cations used by most people are these simple ones like butylammonium, so just an alkyl tail with an ammonium group. They don't really do anything, let's say. So what we wanted to do is design an organic molecule which is very rigid, like this fused ring system, a molecule called benzothiophene, BTBT. It's also interesting for charge transport reasons. People working in molecular electronics know that this is a quite good Hall transporter. But for this story, it's not so important. The fact that it's a rigid molecule and a fused molecule is more important. So what we did is we designed a multi-layered perovskite. So NS2, so 2 inorganic layers per organic layer. And the small cation is in this case cesium. So an inorganic, fully inorganic framework, and then with an organic layer of BDBT in between. So going directly to the interesting part, if you put these 2 films in a desiccator at a very high relative humidity, 77%, so quite harsh conditions, then you see that the reference, it starts to degrade already after 1 day from the NS2 to the NS1, and then over time it completely degrades into a hydrate phase and lead iodide, which is a very typical behavior for these perovskites. While the one with the BTBT, it remained stable for more than 152 days. That's just when we stopped for this study, because you can keep on going, of course. But after the study, we kept it in this environment for more than a year, and it's still unchanged in absorption spectroscopy. So just changing the organic makes a huge difference in the stability of these materials. You can also do it via X-ray diffraction, of course, because absorption spectroscopy, that can hide maybe some things. But also in XRD, you see the same, that the reference, it degrades immediately via a very complex pattern of different phases. The one we designed, it's unchanged over this course of 152 days. So again, also in XRD, you see that these materials are very stable under moisture, which is not very typical for these halide perovskites. And so we wanted to investigate why that's the case. And if you look at the simple contact angle measurement, so just a drop of water on top of this film, you see with the reference that the drop spreads out immediately. So it's a very hydrophilic surface. It degrades the material underneath even. While with this BTBT, it just stays on the surface with a quite high contact angle, which means that actually the surface has become hydrophobic. And we hypothesize that these BTBT molecules they terminate the perovskite surface. They are at the air interface and protect the inorganic framework underneath. And this is the reason why they are so resistant to moisture from the air, because they actually repel water, which is a quite special case for these perovskites. It's not only moisture stability, also temperature. So if you look at these in situ X-ray diffraction as a function of temperature, you see that the reference material starts to degrade at 150, let's say, 150, 160. And the one with the rigid molecules is almost 100 degrees higher temperature. Okay, you may say your electronic application will not reach 200 degrees, but it's a kind of accelerated aging. If it survives until a temperature of more than 200, it will also survive for a longer time at 85. And as you may know, a solar panel exposed to high sunlight, it reaches 85 degrees. So also in temperature stability, you can usually improve the stability by tuning the right organic molecule. And then, of course, we made a new material. It's still for optoelectronics, so hopefully the stronger stability doesn't destroy the optoelectronic properties, and it's not the case. So we made a very simple lateral photodetector, just evaporating some gold electrodes on top, applying a bias, and there you see that, the external quantum efficiency of the new material outperforms the original one, so it performs better. Of course, with such a photodetector, the EQE is dependent on the bias voltage that you put on it. And so it's always a relative measurement. The higher the bias voltage, the higher the EQE becomes. But at least we were quite satisfied that the more stable material does not perform worse than the reference. So that was a quite quick measurement. So some take-home messages for my presentation. So firstly, I think we can say that hybrid perovskites are quite exceptional semiconductors with a very wide range of possible applications. The 2D perovskite subclass is promising because of their enhanced material stability and also their quite great structural flexibility. The internal band alignment really plays a key role in the optical and electronic properties. And molecular design can really make these materials much more stable. So with that, I would like to thank all my previous and current collaborators from different universities and you for your kind attention.
Hi, thank you for your talk. I'm just curious, I would like to have a general comment about the part in which you talk about the energy charge transfer between, the organic part and the inorganic part. So in general, which is the limit between, in which the system, you can consider the system completely mixed with the organic part, so the methyl ammonium lead iodide, okay. And when you start to talk about some, donor acceptor system, okay. And in this picture, so when you have a donor acceptor system, this system should hinder in some way the efficiency of a solar cell. No, if you grow the bidimensional system in a vertical orientation, between the cathode and the anode, because on the other side you have a problem. You separate efficiently the charge, but the charge remain at the interface between the inorganic and organic part.
Yes, indeed. Yeah, so that's a completely valid argument. Indeed, if you would have perfectly horizontal crystal, let's say, you would indeed expect that the fact that you separate these charges hinders the charge transport in a device with electrodes on top and at the bottom. That's completely true. But of course, you have in a thin film crystallites of all different orientations, and then in a combined fashion, it still generates more charges than in the fully confined system, where you have, of course, this very high exciton binding energy of 400 MeV even. But indeed, it's a very big challenge for these pure 2D layered systems to grow them in a vertical way. So if you could solve that issue, then you would for sure hugely increase the performance of these materials in solar cells in all devices where you have out of plane transport, let's say. So yeah, it's a very valid comment. Yes.
Thanks for your presentation. I just have a question about the new molecule that you showed for the two-dimensional in comparison to the PI. It seems the DS space is more higher respect. So it's not any condition to going to lower dimension than 2D, to 1 dimension or 0D.
No, but the D-spacing, okay, so the D-spacing is almost exactly the same as you would have two of these molecules really stacked on top of each other, so forming a bilayer. Of course, because these, like for example in this one, just the length of this molecule, if you make a bilayer, you will separate the inorganic to a much higher extent, and if you count twice the length, you come almost to this D-spacing that we have here. And another argument is the fact, like if you look at excitonic peak position, 550, and if you look at excitonic peak position of the other one, the reference, it's also around 550. If you would have a lower dimensional one, like 1D, 0D, the excitonic peak would shift to 400 nanometers, 300 nanometers. So the fact that you have the excitonic peak at the expected position, it kind of proves that it is a 2D system and not a 1D or a 0D system. But of course, it's true, especially the length is not such a problem. The length, it's the width. If you keep on increasing the width of these molecules, at some point you will go to 1D, 0D systems. So it's not, you don't have an infinite library that you can use. You need still to take into account, especially the width of the molecule. The length is in principle unlimited, but you cannot go to very wide molecules because then you will reduce the dimensionality to 1D, 0D, which become, okay, there are other applications in emission, but for sure not for solar cells or anything like that, because you will confine your charges more and more. But in this case, okay, this is now an example where we don't have the crystal structure, but of course, if you have the crystal structure via single crystal X-ray diffraction, for example, then you can prove that it's a real 2D perovskite and not something else. But it's indeed something that you need to be careful of if you are going to design this kind of bigger molecules, that you don't go to even lower dimensionalities. So that's a good point.
Thank you. And I think this pi stacking, internal pi stacking, is making more strong against the temperature. But
Yes.
this pi stacking is not out of the plane versus for the using in the perovskite, for example, in the make a barrier for the hole or electron injection. Because this pi star is going to the other dimension, no?
Yes, but yeah, of course, this is just a picture, let's say. Typically what you have in the real structure that you have some angle, so that they stack in a certain, not exactly like this or like this, but in an intermediate form. But yeah, the detailed packing of these molecules can be quite complicated. So this is just a very schematic picture. If you have the crystal structure, you see how exactly they are oriented. But indeed, is also a valid comment for sure.
Okay, thank you.
Okay, thanks. Do the premiation after. Okay, thanks. Okay, now, so Udo was introducing the 2D. Now we move to King 5 Mac, that is a giant in 2D Materia. It was discovered, introducing the molybdenum disulfide some years ago, and then, I mean, this large number of discovery and science, actually, in the field of 2D material. So it's a pleasure to invite on the stage King 5 Mac. King.
Well, thank you very much for the introduction. It's a great honor to be awarded this prize, and also really fortunate to have this opportunity to visit the CNR for the first time. It's a great pleasure. So today I think I'll switch gear to talk about something more physics related. So I'll be talking about some of the fundamental physics problem that we can try to address using a class of material that we call moire materials. So I'll tell you a story how we can actually create a moire pattern in semiconductors and use it to create some magic in this kind of materials. Okay. All right. So my story starts with this particular material, the transition metal dichalcogenides, TMD semiconductors. This is the structure of the material. And actually, it's simpler to look from top-down view that it actually looks like a honeycomb lattice structure. If you're familiar with graphene, it actually has the same structure as graphene, except that the immersion symmetry is broken in this crystal structure. And it's a semiconductor, so it actually has 2 copies of direct energy gaps at the K and the K prime point of the Brillouin zone. So compared to many semiconductors, the electronic states of interest are actually not located at the gamma point of the Brillouin zone, but rather they are located near the corners of the Brillouin zone. Okay. And the energy gap here, we are talking about 1 to 2 electron volt. And for the intrinsic material, the Fermi level is actually located in this 1 to 2 electron volt energy gap. All right. So this material is actually quite interesting. It's discovered about 15 years ago, and people actually have demonstrated that you can realize atomically thin transistors, and people are actually still pushing what they can do with this kind of transistors. And it's a very interesting platform to explore 2-dimensional exciton physics. And our previous speaker already talked about excitonic effects, and the excitons in this type of materials are very strongly bound. So it's actually very interesting to explore these strongly bound excitons. And it has very interesting optical and optoelectronic properties. And also it has interesting topological properties that I will talk a little bit more about. It carries Berry curvatures and Berry dependent properties. Okay, so the materials themselves in the monolayer form are already very interesting, but actually can we make them more interesting? So this is the kind of questions that I would like to address in this talk. So for instance, can we make them intrinsic magnets, right? These materials are non-magnetic, but can we make them magnetic? Can we realize the quantum Hall effect without a magnetic field? Can we turn the semiconductor into a superconductor, for instance? And even better, maybe make it a high temperature superconductor. Can we fractionalize the electrons without a magnetic field? You know, the fractional quantum Hall effect that you apply a very large magnetic field, you can fractionalize the electrons due to interactions, but can we do that without a magnetic field? And lastly, can we realize all of this in one system, right? So that would be nice. And so this is the kind of question that we would like to address. So the way that we do it is actually inspired by the discovery of twisted bilayer graphene in 2018. And so similar to graphene, you can actually create a moire pattern in this material. For instance, you can use two of the same materials, for instance, tungsten selenide on tungsten selenide, give it a twist angle theta here, like this, then you actually can create a moire pattern, a superlattice structure. And the period of this lattice, A sub m here, is equal to A, the original lattice constant of the material, which is angstrom level, divided by theta, so that you create actually a period that is much longer than the original lattice constant. We typically deal with a period about 10 nanometer. Another way to create a moire pattern is to actually use two different materials, and you don't need a twist angle in this case. For instance, you angle align the tungsten selenide with tungsten sulfide, even with no twist angle here, you still create a moire pattern. The reason is actually because of the lattice mismatch between the two materials. And in this case, actually, the moire period is given by A divided by delta, and delta is the lattice mismatch. And delta is about 4% in this combination, and that will give rise to a moire period also on the order of 10 nanometer. Okay. And these moire lattices are real. You can actually directly see them in the electron microscope. And for instance, this is the work with Dave Muller's group at Cornell. This is a STEM image of this particular moire material, molybdenite, angle aligned with tungsten selenide. And the small dots here, you actually can see that they are the real atoms. They are angstrom level. But on top of that, you can actually see the emergence of superlattice structure. With the unit cell actually is enclosed by these white dashed lines here. Okay, so now let me highlight a few of the generic properties with this emergence of a new superlattice structure. And first of all, in this limit here, it's particularly easy to deal with the physics. So as long as we're talking about very small twist angle or very small lattice mismatch, then the moire period is much longer than the original lattice constant. So to a very good approximation, we can forget about the original lattice and just treat the electrons move in a smooth periodic potential defined by this moire lattice. Okay, so we can forget about the atoms completely. And the effect of that is the following. You remember that we have a direct band gap in the original material in the big Brillouin zone. And with this smooth periodic potential, we actually can do a zone folding into a smaller Brillouin zone. We call it a mini Brillouin zone. And then the extra Bragg reflection due to the superlattice structure will create this series of flat bands. So you basically go from a band structure like this into a series of flat bands like this in a much smaller Brillouin zone. Okay. And second, actually, the system is a highly tunable system. And actually, you can think of the system the following. You can think of it as an array of moire atoms. Now the atoms are no longer angstrom big. Instead, they are actually 10 nanometer big each atom. So they are much bigger artificial atoms. And the electrons can be trapped by the potential of this array of artificial atoms. And this material, actually, you can think of an artificial material with a density of only about 0.1% of the real atomic density. Okay. In a typical device structure, we have our moire sample sandwiched between boron nitride. Boron nitride are very good insulators. They have like a 7 electron volt band gap. So it's a very good insulator. And so they are actually acting as a gate dielectric. And on top of that, we also put extra metal electrodes to create this kind of capacitors in series structure to be able to tune the density continuously in the material by just applying voltages right to the gates. And because of the much smaller atomic density in this kind of artificial material, now with this kind of gate, you can move the Fermi level through multiple of the flat bands, which is something that you cannot really do in real materials. You cannot really use a gate voltage to tune the Fermi level in real material, not even through one band, right? But here you can do through multiple flat bands. And finally, I want to say that the electrons are intrinsically strongly correlated. Let me explain what we mean. So the electrons have kinetic energy, and which is of this form here. The kinetic energy of non-relativistic electron is proportional to the momentum square, and as a result, the moment is proportional to 1 over the moire length scale squared. Okay, and typically we are talking about 1 to 10 milli electron volt kinetic energy, which you can think of it basically is the width of this band. One of the band here is the kinetic energy. The Coulomb repulsion energy, we can take it as the Coulomb form here, and it's proportional to 1 over the Moray period. And typically is about 100 milli-electron volts. You plug in the numbers. And strongly correlated means the following, that if you take the ratio of the Coulomb repulsion energy divided by the kinetic energy, it's proportional to the Moray period, and typically we are dealing with a factor larger than 10. So the Coulomb repulsion energy is very strong compared to the kinetic energy. And you would expect that in this kind of limit, the band theory typically fails, and we really have to deal with a many-body theory for the electrons. Okay, so with this introduction, I would like to just give you 2 brief examples of what we can do with this particular type of material. First, I will tell you how the material can be used to mimic the Hubbard model, and we actually can use it to observe the phase diagram of a high-temperature superconductor. And if time allows, I will also tell you a little bit about how we can actually fractionalize the electrons without a magnetic field in this material. So first of all, let me go back to this picture of an array of artificial atoms, and the electrons are trapped, but they can actually still hop around. And the hopping rate is actually this T, which is the kinetic energy of the electron here. They can hop between neighboring sites, and if you end up with the 2 electrons on the same site, they would Coulomb repel each other strongly, right? So that is actually cause a Coulomb repulsion energy of U here. And it's shown by this paper here that as long as the bands are non-topological, I will explain a bit more later on, and this actually realized something called the Hubbard model, which is a very famous model that tried to capture the effect of electron-electron interactions in solids. And there are only 2 terms in this Hubbard model. One is the kinetic energy of the electron. The other is the repulsion, the Coulomb repulsion for the electrons. Okay, so at the beginning of this field, we actually did not know how to make electrical contacts to this type of material. So we invented a technique to measure the electronic states of this material. And let me briefly explain how it works with this technique. We call it the exciton sensing technique. So let's consider, again, a monolayer of this semiconductor. We should light to it, and that would generate an electron-hole pair, and they will bond to each other, form an exciton, like the previous speaker talked about already. And these are the electrostatic field lines that bound the electron and hole pairs together. And you actually can see that these 2-dimensional excitons, most of the field lines responsible for binding actually live outside of the material, not inside. Okay, and this is the binding energy of the exciton. It's a long expression, but the important thing I want to point out is actually that the exciton binding energy is actually sensitive to the dielectric constant of the surrounding environment, because the electrostatic field lines live mostly outside of the plane. And this is a schematic absorption spectrum of this type of material. You can see the 1s Rydberg state, 2s, 3s, 4s, and so on and so forth until you hit the band gap here. The difference between the 1s energy and the band gap, that gives you the exciton binding energy. And we are talking about half an electron volt of binding in this type of material. Okay, so let's see how we can actually use this property to sense states in strongly correlated electrons. So let's now imagine if I have a sample, we can put very close to the material, to this semiconductor layer, but not touching it. And if the sample is metallic, that would actually increase the dielectric constant of the environment. And as a result, that will reduce the binding energy of the exciton. If the sample is actually in some insulating state, that would reduce the dielectric constant of the material. And as a result, that would actually increase the exciton binding energy. So by just measuring the exciton binding energy of the sensor layer without ever really probing the sample, you actually would know what's happening inside the sample. Okay, so that's how it works for this technique. And so with this idea, we actually build a device. The device is a little bit complicated. Again, this is a sample. Well, sorry, this is a sample here. Sandwiched by the gates. The gates allow us to tune the electron density in the sample. But very close to the sample, we actually put a sensor here that we can excite this electron-hole pair. And we make sure that the 2 are very close to each other such that the field lines can penetrate through the sample. Then we can actually use it to do sensing. All right. And long story short, this is the result. This plot is a little bit busy, and let me just explain to you. And this is the photon energy we should light onto the sensor to do spectroscopy to sense what's happening in the sample. So this is actually the photon energy with the focus to the 2s Rydberg state of the sensor. This is the gate voltage that tunes the electron density in the sample, not the sensor. The sensor is always charge neutral. Positive gate voltage means electron doping. Negative gate voltage means hole doping. So on this side, we put holes. On this side, we put the electrons in the system. And every time you actually see a bright spot here with a blue shift in energy, actually that means a stronger excitonic effect and a larger exciton binding energy. That corresponds to each of these bright peaks here corresponds to an insulating state. The background there corresponds to metallic states. Okay. So let's take a look at the simpler example of these states. For instance, we have this state here with filling factor 1 and filling factor -1 here. And the notation is actually that you fill 1 electron per triangular lattice site in the system. So that corresponds to a half-filled band in the system. And the filling factor 2 and -2 corresponds to filling 2 electrons per site. So that's why you have 2 arrows here. And that corresponds to a fully filled band. Let me explain a little bit what these insulating states are. If you have a filling factor 2, you have 2 electrons per site, and that corresponds to a fully filled band. Then just by band theory, it's an insulator. It's just a band insulator. It's an insulator due to Pauli exclusion principle. On the other hand, if you have filling factor 1, which corresponds to 1 electron per site only, that corresponds to only a half-filled band. Without any interaction, it should not be an insulator. The band theory tells you that it should be just a metal. But of course, we are in this limit here. The U over T is very, very large, and that will automatically open up a Coulomb gap in the system to save some energy. And basically, what's happening is actually that the electrons, rather moving around, they are totally localized due to the Coulomb repulsion with each other. And that's actually the lowest energy configuration to the electrons. And if they move around, you cause more Coulomb energy, and that's actually not energetically favorable. And we also verified that there are indeed local moments emerge, but I will skip that part. Okay. So I think we have a pretty good understanding of what's happening at filling factor 1, filling factor 2, and -1 and -2. And very briefly, you can also see that there are lots of insulating states with fractional fillings, for instance, 2/5, 1/3, 2/3, 1/4, and et cetera, right? Each of this bright peak here is one of these insulating states. And what's happening is actually that is, again, the strong Coulomb repulsions between the electrons do the magic. And because of the longer range Coulomb repulsion of the electrons, they actually self-organize into a crystal structure. And these are called the Wigner crystals. And for instance, the electrons at 2/3, they would form a honeycomb lattice structure. At 1/2, they would spontaneously form these trifaces, break the rotational symmetry of the crystal, and which can also be verified by an optical birefringence experiment. But I will skip this part as well. Okay, so what I have been telling you is actually the limit of very large U over T limit. In this case, the electrons have very little kinetic energy, and the bands are really, really flat. And in some sense, the electrons are essentially classical objects. They just, a particle carry a charge. And that's why it's a very good platform to study the small insulation and the Wigner crystals. But on the other hand, if you actually want to create superconductivity, you would like the electrons to be more quantum mechanical, right? So the idea then, you actually, to make the electron more quantum mechanical, you want to increase the kinetic energy. And as a result, to reduce the U over T ratio, maybe you get a chance to induce superconductivity in the system. And that's something that I want to very briefly highlight. Indeed, by doing that, we can get a superconductor out of the system. So the idea is to reduce the U over T ratio. And if you remember from a few slides ago, the U over T is proportional to the Moray period. And so to reduce the ratio, we actually want to reduce the Moray period. And the Moray period is proportional to 1 over the twist angle, so you want to increase the twist angle in the system. But we can do that in our material, right? You can continuously tune the twist angle without a problem. And so this is actually a device. Now I'm switching from optical probe to electrical probe. This is actually the twisted sample, which are directly connected to these electrodes here, that we can measure the resistivity of the sample quantitatively. Also with the gates, so that we can actually tune the density also continuously. So let me just give you one example. By just reducing this U over T ratio here, this is the kind of phase diagram that we can get. By just tuning the kinetic energy roughly the same as the Coulomb repulsion energy, and what I'm plotting here is the resistivity map. as a function of temperature and the doping density in the system. And this is filling factor 1 that corresponds to 1 electron per Mole unit cell or half band filling. This is in log scale, so that when you see the very blue region here, that means nearly zero resistivity. When you see the red here, that means very high resistivity, like an insulator, okay? So long story short, we have a mod insulator at half band filling. You dope a little bit away, you kill the anti-ferromagnetism, and you get 2 superconducting domes coming out that has zero resistivity. And when you dope further away, you recover the usual Fermi liquid behavior. And in all these regions, the white region here, you actually get strange metal behavior that the resistivity scales linearly with temperature, okay? Basically, this long story is short is that by just making the kinetic energy of the electrons comparable to the repulsive energy of the electron, we can actually create a phase diagram that look pretty much like the high temperature cuprates, if you have looked at it. And the Cooper pairs are tightly bound in the sense that the Cooper pair size is about the same as the inter-electron distance. And so I think our study actually established that the Hubbard model, established a Hubbard model simulator for trying to solve the high TC problem, okay? All right, in the last maybe 5 minutes or so of the remaining time, I will highlight one last thing that we can do and how to fractionalize the electrons without a magnetic field. And these are the people involved in the work. And so far, what I've been telling you is actually that the flat bands are non-topological, meaning that they carry 0 Chern numbers. Okay, so these are the flat bands. This is the example that I told you. But now imagine actually if you have a flat band from one of the layers and the other flat band from the other layer, then you can use an electric field applied perpendicular to the sample to control the distance between these 2 bands through the Stark effect, right? And in fact, you can actually use an electric field to create a band inversion to totally invert the band, and then the band will become topological. That means that they actually carry a finite Chern number. And you can do that in heterobilayer by applying a very large electric field, or you can actually do that also in homobilayer without any electric field, because the 2 layers, the electronic bands are already degenerate, and in a sense, they are already inverted. And indeed, these are the series of theory calculations that if you look at this particular material, a twisted bilayer molybdenite, and what they have predicted is a series of flat Chern bands in the system at each of this value, K and K prime. And on K, you have a Chern band of Chern number all equal to +1. On K prime, the Chern number are all equal to -1. And what does it tell you? It tells you the following, that they actually look like Landau levels. And if you remember, in 2-dimensional electron gas, if you apply a perpendicular magnetic field, a high enough magnetic field, you create these perfectly flat Landau levels that they carry chiral edge state that give rise to the quantum Hall effect, right? But here, you actually do not need any magnetic field. You create this kind of Landau level-like bands in the system. And the interesting thing is the following, that the electrons in the K valley will experience a positive magnetic field, and in the K prime valley, it will experience a negative magnetic field. So the material actually realized a pair of time reversal conjugate Landau levels without any magnetic field applied to the system. Okay, so now let me just give you an example, then I'll wrap up. And we look at this particular material, twisted molybdenite at 0 magnetic field, and we look at the electrical transport properties. Let me show you first this result is a 2-terminal conductance measurement, conductance versus the hole filling factor. And again, 2 holes means 2 holes per Mole unit cell in the system. And you can clearly see conductance plateaus in units of E²/H, the conductance quantum, at filling factor 1, 2, 3, 4, and 6 here, okay? And we can also measure the 4-terminal resistance in the same device. And this, at the top panel here, is the Hall resistance. At the bottom is the longitudinal resistance. And actually, you can see a quantized Hall effect without a magnetic field, and the 0 resistivity at filling factor equal to 1, and nearly quantized at fractional fillings, 4/3 with a resistivity dip, and also the Hall resistance to be 0 at the other fillings, 2, 3, 4, 6 here. Okay, this is a summary, and I'll skip. And so let me just tell you very briefly what's happening. What's happening is actually that at filling factor equal to 2, that corresponds to a fully filled conjugate pair of bands. And each pair of this band will contribute a 1 chiral edge state. But this one will contribute a chiral edge state this way, clockwise. And this one band will contribute a chiral edge state counterclockwise. So you actually get two pairs, two chiral edge states that actually counter-propagating. And at filling factor equal to 2, you get a quantum spin Hall insulator. Okay. At filling factor 4, you fill two pairs of these states, then you get a double quantum spin Hall insulator, and so on and so forth. And that's why you actually get a two-terminal resistance or conductance of 2e squared over h, 4e squared over h, and 6e squared over h with 0 Hall resistance. At filling factor equal to 1, it corresponds to a half-filled band without any interaction. It would be a metal again. But because of the interaction, it will spontaneously polarize to one of these flat bands here. Then it actually makes it a quantum Hall system that carries 1 chiral edge state, and that's why you actually can measure a fully quantized Hall resistance without any magnetic field. This is 0 magnetic field, and with a vanishing longitudinal resistance. So this is known as the quantum anomalous Hall effect. Anomalous means you don't need a magnetic field. Okay. A fractional filling, that's actually quite interesting. It's even more exotic because without any interaction, it's still a metal, but with interaction, it will spontaneously polarize to one of the values here, and it also opens up a gap at the system, and this is known as the fractional Chern insulator, and that explains why you actually get a fractionalized value of the resistance quantum and a resistivity dip here. And historically, actually, the fractional quantum anomalous Hall effect was discovered at filling factor less than 1 here from both thermodynamic measurement and from direct transport measurement. And I just want to briefly highlight that, instead of the quantization to a fractional value is very important. It's not just, some simple extension of the integer physics, because what that means is actually that the electrons are now carry fractional charge and fractional statistics. And all this actually can happen without a magnetic field. And so that's really something that is very interesting to be further explored, in particular for the application in topological qubits. And I think I'll skip this last part for the interest of time and go to this conclusion here. So I hope that I can answer this question, that can we actually do some magic in the semiconductors? In particular, can we realize all these systems in semiconductors? And I hope to convince you that the answer is yes, and the way is through Moray engineering. And because of the interest of time, I actually did not have the time to talk about other examples. For instance, the material can also realize other strongly correlated Hamiltonians, such as the the Kondo lattice Hamiltonian, the Hubbard model for bosons, not for electrons, and also the bosonic Chern bands in the system. So that, I think, with with this very rich system, that will keep us busy for the next few years. And with this, actually, importantly, I need to really acknowledge the people in the work. I collaborate through all these years with Professor Ji Shan, who's also sitting here in the audience. And we are very lucky to have this group of very talented graduate students and postdocs. And I acknowledge Alan McDonald and Bai Elsa for theory supports, the TMD crystals from Jim Holmes' group, and also the boron nitride crystal is from the very famous Japanese group. For those people who are in the business here, and these are the two gentlemen that we need to know. And here are the funding sources, and thank you for your attention.
When you were sensing the X-nodes, okay, what should be the full width maximum of the X-node? It should be the line should be very, very strict, and very, the width should be very limited, because otherwise you can have a resolution of millions. Okay, what should be it's a width of the X-node?
Yeah, actually, it's you mean the line width of the excitons, or what? Yeah, I think this is very much related to which Rydberg state you use to sense. So, for instance, the 1s Rydberg state has a very small ball radius. So basically, you want to put the sensor and the sample distance to be within the ball radius. And for the 1s state, the ball radius is 1 nanometer. So it's very hard for you to actually put the sample. Basically, you have to directly touch it. So in that case, and so that's why we actually use a higher energy Rydberg states, for instance, the 2s state or the 3s state. And the ball radius becomes significantly bigger. For instance, the 2s state has a 5 nanometer ball radius. Then it's pretty easy to actually put these two within 5 nanometer distance. And so the sensor can penetrate through the field line can penetrate through the sample and do the sensing there. And also how much a change you can observe in this system depends on the choice of your Rydberg state and also the distance, right? If you put them closer, then you will have a stronger sensitivity. Then you will see a bigger shift, right, in any of this, yeah. Yeah.
So you were showing this, magic angle, which is fixed, but you can also dynamically change this angle and then to adapt new physics.
Yes, actually, that's an interesting question. Dynamically, you mean in real time, right? Yeah. So maybe the more promising approach is to excite a particular, maybe a shearing mode or some kind of mode like this that can change in real time, maybe on the order of several picoseconds or something, that you can actually change the twist angle by a little bit, and that actually could have a strong effect on the correlated states of the electrons, right? Because by changing the twist angle, you're changing the Moray period, and you can actually see that the Moray period, the kinetic energy of the electron is strongly dependent on the Moray period, right? Yeah, yeah. Okay, okay.
So your question has been. Okay, thanks. So I now let's move. I ask my presentations. Okay. Okay, now, so now it's time to move to the award. I invite also the site managers. Where are the site managers? Daniele and Tonino. So I believe there is no the site manager of Trieste today with us. Because now I believe also we need some the prize. Where is the prize? Okay. There is no prize. Okay. There is the prize. Okay. Okay. Good. Okay, so let me announce the first one. So for the breakthrough achieved in the last 5 years, really a pleasure to award Wouter van Gombel for the junior category PRISM Award 2025. Let's move here.
Thank you so much. It's really very nice playing. Thank you.
Some additional contribution.
It is a very good wine. From Lucania.
Okay, now let's move to the senior award for the breakthrough achieved in the last 5 years, but also before, but especially for the last 5 years. It's really a pleasure to award King Fai Mac for the PRISM senior category 2025. Okay, so then, I mean, the celebration, thanks for the site managers, and thanks for all of you, and I would like also thanks also the jury, the international jury that was working very heavily. This summer was July and August working and digging among all the many nominations we have this year. It's a very difficult task. And I also thanks all of you. I thanks the winners of the PRISM. So you know that, I mean, you will be part of jury next year. So so you have a very big responsibility as well. And also the PRISM prize also entitle you to start some activity with the researchers of the Institute. We provide you to the support of Institute with our Tempism platform, and then any kind of form of collaboration can find. I mean, we will heavily support this kind of interaction between the Institute and the winners. So thanks really a lot to all of you. And last but not least, we can move now to make a brindisi all together and to celebrate the winners, and also to say hello for the Christmas, the New Year time that we are celebrating in a few weeks. Thanks a lot.